One night in 1669, a German alchemist named Hennig Brandt was searching, as he did every night, for a way to make gold. For some time, Brandt had focused his research on urine. He was certain the golden stream held the key. Tonight, his patience would at last be rewarded. He had boiled the urine down to a concentrated paste. Now he subjected it to intense heat. Was this the legendary elixir that would turn lead into gold? Alas, it was not. Brandt had stumbled on the element phosphorus. This is how the discovery of elements began, with people trying to turn the substances of nature into something useful or valuable. But people are naturally curious, so as they worked with these materials, they began to wonder, what is this stuff? What is the world made of? Thousands of years ago, the Greeks proposed that the world is actually made of just 4 elements in combination: air, water, earth, and fire. Today we know that matter actually comes in more than 100 distinct varieties, neatly arranged in the periodic table of the elements. But for most of history, matter was a profound mystery, a 2,000-year detective story in which people across the world were trying to identify the elements and figure out how to use them. It's an amazing story filled with unforgettable characters. In this series, you'll meet 7 extraordinary scientists whose findings drove the search for the elements. So join me as we retrace the steps of these chemical detectives as they struggle to solve the mystery of matter.
Eh bien, chers amis.
Major funding for The Mystery of Matter Search for the Elements was provided by the National Science Foundation, where discoveries begin. Additional funding provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education, and by the following.
One of the first big clues in solving the mystery of matter came from the discovery of the most immaterial stuff you can imagine: air. Of course, people have always known about air. They could feel the wind on their faces and see its powerful effects in storms. What they didn't know was that there's more than one kind of air. That changed in 1754 when a young Scottish medical student named Joseph Black set out to find a cure for kidney stones. He poured acid on this chalky substance and trapped the air that came out. To his surprise, this air didn't behave like air at all. It was heavier than ordinary air and promptly put out a flame. Black's discovery of fixed air, what we now call carbon dioxide, was a turning point in the history of science. People had long known about liquids and solids. Now, suddenly, they realized there was a third state of matter: gases, of which air is just one example. Over the next 20 years, the exploration of this new dimension would transform our understanding of matter. After Black's discovery, British scientists quickly identified 2 more new gases: hydrogen and nitrogen.
And then in the early 1770s, that astonishing investigator Joseph Priestley discovers all sorts of new airs.
Priestley was a minister by trade, but also an amateur scientist, what was then called a natural philosopher.
He was a great dabbler in things and was constantly getting obsessed with new fields.
Fields like the new science of gases.
Priestley's style of science is very interesting. He's a kind of inspired forager. He's basically messing around with different things to see what will happen. One of the things Priestley did was to pour acid on everything. He collected those bubbles, tested them thoroughly, and discovered all sorts of amazing properties.
By messing around in this way, Priestley discovered 9 new gases, more than anyone else in the world.
He was very much open to chance discoveries. He would stumble across things and he would follow his instincts, and he was always looking for these kind of fortuitous accidents.
One such accident happened in 1767 when Priestley was assigned a new congregation.
They put him in a house that happens to be right next to a brewery, and this turns out to be an incredible stroke of good luck. Priestley, being the constant investigator that he was, would kind of pop over and see what was going on at this brewery.
Just above the vats of beer, he discovered a haze of carbon dioxide bubbling up from the fermenting brew.
And he decided he wanted to do some experiments with their beer. Well, fortunately, they said yes.
Priestley found that if he simply poured water from one glass to another over the surface, the water would absorb the gas rising from the beer. The result was refreshingly bubbly. By 1772, he had invented a better method, generating carbon dioxide and injecting it directly into water.
In the space of 2 or 3 minutes, I can make a glass of exceedingly pleasant, sparkling water. You can't tell the difference between this and natural mineral water.
Priestley had invented carbonation. Remember that the next time you enjoy a soft drink. But with this act, he also set in motion a series of improbable events that would soon overturn our understanding of matter. It began when a British doctor suggested Priestley's windy water might be effective as a treatment for scurvy, a disease that plagued sailors on long sea voyages.
Scurvy was a huge problem for the military during that period, and so the idea that there was this potential solution that it also happened to be a tasty beverage was appealing.
In 1772, Priestley addressed Britain's leading scientific organization, the Royal Society, and published a pamphlet describing his method for making soda water. He urged the British Navy to test the potential cure. Quick to pick up on this development was a defrocked Portuguese monk named João Jacinto de Magellan. A distant relative of the great Portuguese navigator, he was now serving as a French industrial spy.
Magellan is in the employ of the French government and is there basically scouting out the Royal Society for interesting items that he might be able to bring back to his bosses.
Sensing a potential military secret, Magellan alerted his handler back in France, Commerce Minister Jean-Charles Trudaine de Montigny.
Trudaine was interested in science, was a member of the French Royal Academy of Sciences, and immediately saw the possible value of this.
Trudaine, in turn, called on one of France's brightest young chemists, Antoine Laurent Lavoisier.
Et qui en est l'expéditeur? Monsieur Trudin de Montigny. Monsieur Trudin de Montigny. Oui.
I know your precision when it comes to physics and chemistry, and I'm giving you a chance to be of service to your country. Please repeat these experiments and add your own observations. The value of these discoveries depends on our moving quickly. I hope you will not be long in getting this little work done.
Trudaine probably intended this politely phrased letter as an order rather than a request. Lavoisier really couldn't ignore it.
Though soda water would turn out to be useless against scurvy, this pointed suggestion by a government official acting on a tip from a Portuguese spy would set Lavoisier on the path toward his greatest discoveries. Born into a well-to-do Parisian family, Lavoisier had received a fine education and taken a degree in law. Now 28, he had joined a consortium that collected taxes for King Louis XV.
As a result, Lavoisier became a very wealthy man.
But his true passion was chemistry. Lavoisier spent 3 hours in his private laboratory before work every day and returned there after dinner, often accompanied by his young wife. Marie-Anne Pultz was the daughter of one of Lavoisier's business partners.
Antoine?
Oui?
She was just 13 when they were married, but bright, outgoing, and mature beyond her years.
Lequel est-ce que tu préfères?
Marie-Anne was virtually his collaborator. She knew English, learned chemistry, assisted Lavoisier in the laboratory. She was an extraordinary person. Had she lived in our own time, she probably would have become an outstanding scientist in her own right.
One of Marie-Anne's most important roles was to create the diagrams and illustrations that accompanied her husband's published work.
Marie Lavoisier's drawings give us the eyes to look directly into Lavoisier's laboratory. We can see the people, we can see the devices, we can see the arrangements of those devices. We can understand what Lavoisier did so much better because of what Marie drew.
Spurred on by Trudaine, Lavoisier eagerly studied fresh translations of Black, Priestley, and other British chemists who had pioneered the study of airs.
The work of these previous experimenters merely hints at what's happening when air is taken up or released by different substances. I shall review all their work, repeat all their experiments, taking new precautions in order to develop a coherent theory. This subject, I believe, is destined to bring about a revolution in physics and chemistry.
What made this new science of air so revolutionary was that it threatened to topple the reigning theory of chemistry, a theory inspired by the mystery of fire. Most chemists believed fire was due to some fiery principle that was given up during combustion. And all our senses seem to confirm this idea. Heat, light, smoke, all are released as the fire burns. By the mid-1700s, this essence of fire had been given a name: phlogiston. Phlogiston was the foundation of chemistry's leading theory for nearly a century because it seemed to explain things like metals and rust. When iron ore was heated in the presence of charcoal, phlogiston from the charcoal fused with the ore to form metallic iron. When the iron was exposed to air or water, the metal released its phlogiston as it rusted. Other metals went through the same process, forming the green verdigris of copper, for example. Ore plus phlogiston equals metal. Metal minus phlogiston equals rust, or what was then called a calx.
Only there was a problem. The calx was heavier than the metal. Even though phlogiston had left the metal, it's lost something and yet it was heavier.
The calx should weigh less than the original metal, but it doesn't. The calx is heavier than the metal.
Though many chemists were aware of this contradiction, they let it pass because phlogiston otherwise worked so well. But Lavoisier was really troubled by this because he was obsessed with the weights of his experimental ingredients.
Lavoisier was very careful to get very good instruments. He probably at one point had the largest and most complete private laboratory on Earth.
With my precision scales, imported from England at great expense, I measure the weight of each substance at the beginning and end of every chemical reaction.
Lavoisier was a master of this balance sheet kind of chemistry. Remember, he was a tax administrator by day. He knew a lot about accounting, and so this kind of ledger keeping was natural to him.
It is a fundamental truth of chemistry that the same amount of matter exists before and after each experiment. Nothing new is created, nothing lost. The whole art of performing chemical experiments rests on this principle.
Today we call this idea the conservation of matter.
When you carry out a chemical reaction, what comes out has to be exactly equal to what goes in.
The total weight must remain precisely the same. If not, there's an error somewhere.
He wasn't the first to assume conservation of matter, But Lavoisier applied this idea more rigorously than anyone had before. And it worked very effectively as a tool of discovery.
The power of Lavoisier's method would become clear in October 1772, when he set out to solve the riddle of why metals gain weight when they form calxes.
Common sense suggested that when things rust, they must lose weight. They fall apart, they become brittle and weak. Lavoisier was interested in actually measuring what happened.
He conducted his experiments in public, relying on a huge burning lens that focused the sun's rays to produce intense heat, while elegantly dressed bystanders watched in amazement. Lavoisier placed a calx of lead mixed with charcoal inside a glass vessel partially filled with water, then subjected it to the intense heat of the burning lens. The result was extraordinary.
As the calx changes back into the metal, it releases a large quantity of air. This air forms a volume 1,000 times greater than the calx it came from.
This startling finding suggested a radical idea. If air came out as the calx changed back into a metal, could it have gone in when the calx was formed? Could air be the reason calxes were heavier than expected? Lavoisier also found that when he burned elements like sulfur, they too gained weight.
There was then no doubt. I realized that the increase in weight occurs because a portion of the air is absorbed into the solid material.
He knew he was onto something very important. He knew that the element did not lose mass, it gained mass. It took up some part of the air.
I felt I must secure my right to this important discovery. So I deposited a note with le secrétaire de l'Académie to remain sealed until I was ready to make my experiments public.
He's discovered what seems to be evidence by weighing things that seem to flatly contradict what the phlogiston theory is predicting.
Despite what our senses tell us, both rusting and burning involve absorbing something from the air, just the opposite of what chemistry's reigning theory held.
It had been known for 100 years that metals gain weight when they become calxes, but no one had bothered to really investigate this anomaly. By focusing so intently on weight, Lavoisier had challenged the very foundation of chemistry, and he'd identified the source of that weight gain. Air was somehow involved.
But was it air itself or some part of the air? And if so, what part? The identity of the mystery gas eluded him for 2 years. He was still stumped in late 1774, but the answer would soon be delivered by Joseph Priestley. By this time, Priestley had begun to study something called the red calx of mercury. Mercury is a strange metal, one of just 2 elements that is liquid at room temperature. But like other metals, it forms a calx, a red solid that pharmacists of the 1700s used to treat venereal disease. Chemists had noticed something unusual about this calx. They could convert it back into metallic mercury simply by heating it. No charcoal, no source of phlogiston was needed. This was theoretically impossible. How could it be? The ever-curious Priestley wanted to know. So in August 1774, he obtained a sample of mercury calx and used his own burning lens to heat it with sunlight.
That reddish substance in turn decomposes, giving back mercury, but also a gas.
Priestley collects this air because he likes to test these gases and to see what properties they have.
If it were his old friend fixed air, the candle would go out.
But what he found about this air was it had quite extraordinary properties.
What astounded me was that the candle burned in this air with remarkable vigor. The flame was bigger and brighter than in ordinary air.
Something in this air seems almost better than normal air, which is very puzzling.
I was utterly at a loss. How could I explain this?
Eh bien, chers amis, buvons à la santé d'Archimède.
Dr. Priestley, have you been to the continent before?
No. This is my first time.
2 months later, on a visit to Paris, Priestley was invited to dine with members of the Royal Academy of Sciences, including Antoine Lavoisier.
J'ai récemment réalisé.
Priestley tells Lavoisier in his very broken French about his new discovery.
Avec les résultats très intéressants. I described this experiment at the table of Monsieur Lavoisier. I never make the least secret of anything I do. Le même air de plum rouge.
Everything that he came up with, every new experiment that he did, even when he wasn't sure what the results meant,
Qu'est-ce que c'est ce plan rouge?
he was constantly sharing that information with as many people as possible.
Mais, à ma grande surprise, I also told them that it produced a kind of air in which a candle burned much better than in common air. Mieux que dans l'air commun. At this, the entire company, including Monsieur and Madame Lavoisier, expressed great surprise. I'm sure they cannot have forgotten these events.
Monsieur Priestley, êtes-vous bien sûr que ce n'était pas l'air fixe?
If you want, I can translate for you.
Ah, merci.
Are you sure that what you found was not fixed air?
Absolutely. But I'm not yet sure of what it was.
Lavoisier did not appreciate Priestley's style. He didn't think Priestley brought very much thought to his scientific foraging.
But Lavoisier was smart enough to recognize that Priestley was onto something and take that piece of information and go back to his lab to figure out exactly what Priestley had discovered.
Could this be the gas he was looking for? The one involved in rusting and burning? Lavoisier hurried to the local apothecary to buy his own sample of mercury calx.
Now, tricky part.
Back in England, Priestley dithered for months on other projects,
Look what you can do.
unaware he was in danger of being scooped. Finally, it occurred to him, if this gas he had discovered supports fire, might it also support breathing?
Here we have one of the great discoveries in the history of chemistry, and the scene is kind of amazing. You've got this man and a mouse.
I put a mouse into a glass vessel containing 2 ounces of the air from the heated calx of mercury. If it were common air, a full-grown mouse would have survived in it perhaps a quarter of an hour.
15 minutes pass. 20 minutes pass.
In this air, my mouse remained perfectly at ease for a full half hour.
That's twice as long as any mouse has ever survived.
I began to suspect that the air into which I had put the mouse was better than common air.
He takes the same mouse, sticks it back under the glass, and sure enough, the mouse survives another 30 minutes in this strange new air. He realizes that something fundamentally different has happened. This air is some kind of super air.
I concluded that this air was between 5 and 6 times better, that is, more breathable than the best common air I'd ever tested.
He finally has kind of convinced himself this air must be safe to breathe if the mouse is doing so well. And so he gets up enough courage to actually try it himself.
It doesn't feel any different from common air when I breathe it in. But I feel peculiarly light and easy. In time, this pure air may be useful as a medicine or sold to the fashionable for recreation. Up to now, only 2 mice and I have had the privilege of breathing it.
As Priestley is conducting these experiments in England, across the channel, Lavoisier is basically going through the exact same experiments.
Lavoisier, realizing that this is essentially the key to the mystery, gets to work on it.
3. I found, much to my surprise, that this air had none of the properties of fixed air. A candle burned in it with a dazzling splendor, and charcoal, instead of just smoldering, threw sparks in every direction.
Lavoisier announced his findings with great fanfare at the 1775 Easter meeting of the Academy of Sciences.
All this evidence convinced me that this air is more breathable, more combustible, and more pure than even the common air in which we live.
And he gives it the name oxygen.
In announcing his findings, Lavoisier made no mention of Priestley's revelation over dinner 6 months earlier.
Now, Priestley is not a shrinking violet here. He hears about this and he objects.
He should have acknowledged that my account over dinner led him to try the experiment. One should not put one's scythe into another man's harvest.
I admit I was not the first to do these experiments. That claim goes to Mr. Priestley. But from the results, we have drawn diametrically opposite conclusions. I may be criticized for having borrowed from the work of this celebrated philosopher, but I trust that the originality of my conclusions will not be challenged.
Lavoisier was right. While it was Priestley who made the discovery, it was Lavoisier who grasped the implications of this new gas.
3.
Lavoisier was the only one who understood what was going on. Perhaps he didn't understand perfectly, but the moment that new element, which we call oxygen, was there, he picks it up and he runs with it.
Over the next 15 years, Lavoisier would show that air is not a simple substance, as the ancients believed, but a mixture of two newly discovered gases. That water, too, was a product of two gases, and that fire is not an element, but a process of combining with oxygen. Even the solid substances the ancients had lumped under the heading earth were now seen in a new way.
Metals like iron and tin and lead had been known for centuries. But in the era of phlogiston, they were thought to be compounds because they had phlogiston in them. Lavoisier had turned this picture upside down. He showed that by stripping away the oxygen from the ore, you got down to the simpler metal within. The metal, not the ore, was the element.
So all four of the ancient elements, air, water, earth, and fire, had been abolished, thanks to the discovery of oxygen.
Once you accept the existence of oxygen, the main difficulties of chemistry appear to evaporate. Well, if all of chemistry can be explained without phlogiston, in all likelihood, it doesn't exist.
For years, many chemists, including Joseph Priestley, refused to abandon the old theory. What finally won the day was the textbook Lavoisier wrote in 1789 to spread his new chemical theory. As it was adopted around the world, phlogiston quietly passed into history.
So the old chemical system has been essentially destroyed.
Though Lavoisier is often given most of the credit, it was really both these men, working in their very different ways, who brought about this chemical revolution.
They kind of needed each other in a way. For science to work, you need both kinds of scientists, right? You need the scientists who are great systematizers, and then you need the mavericks and the tinkerers who are going to open up new doors for discovery.
One of the doors Priestley and Lavoisier opened was a fresh way to tackle that old question, what is the world made of? It was clear now that rocks of every conceivable variety might harbor undiscovered elements chemically fused with oxygen.
people realized that if they could release oxygen from other substances, what was left behind might be some of these missing elements that everybody knew must be out there.
How many more elements might you find by stripping away the oxygen that like to bind to so many things?
Lavoisier's textbook included the first modern list of elements, 33 simple substances. Some, including light and heat, were later found not to be elements, but it was a start, and it served as a challenge to other chemists.
Now that they knew how to look for them, chemists began to ask, what are the elements? The question had never been asked before in exactly that way. And so the discovery of oxygen really served as a starting gun for a worldwide race for new elements.
All over the world, chemists and amateur collectors responded to Lavoisier's challenge, rapidly identifying 15 new elements. From Sweden to Mexico, Connecticut to Siberia, the discoveries kept coming, sometimes as many as 4 in a single year. And few things could bring a chemist more glory than identifying a new element.
Was provided by the National Science Foundation, where discoveries begin. Additional funding provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education, and by the following. To learn more about the search for the elements and watch bonus videos on the featured scientists, visit pbs.org/Mystery of Matter. The Mystery of Matter Search for the Elements is available on DVD. To order, visit shoppbs.org or call 1-800-PLAY-PBS.